So now let's look at what we mean by a long channel versus a short channel device, and we'll start seeing how the current equation changes. Okay. So first I'll try to give you an intuition of why the short channel device should behave differently. Okay. I'm going to consider, I'll draw it really exaggerated. Okay. Now this is my source, this is my drain, okay, and this is going to be my metal and oxide. So the channel length really is this. L is N plus P substrate. Okay. Now in order to gain power, speed and other things and also area, people started scaling this transistor, right. So they started bringing the drain end closer to the source end. Okay. Therefore they've just simply pulled this guy as close to this as possible. Okay, N plus, and then my gate, or I should draw this in blue so that it's a different color, N plus, and then I will truncate my gate right here. This is my thing. So this, if you look at it, is my short channel device length. Okay. Now consider the various bias conditions that we can apply on this transistor. Okay, so this is the source. Source is always assumed to be grounded because it's a reference potential by definition. Then I have a gate, right, and I have a drain, VD, and then I have a body terminal here, right. So this would be my body terminal actually, VB. So this is a P junction in contact with an N plus junction, right. That means that there is going to be a small depletion region or a space charge region around this point of contact. So what will happen is I will have a small space charge region like this. Of course on the source side also it's going to happen, right. Because the channel length was so large, it really did not matter whether I considered the channel length up to this depletion region edge or up to the N plus region, because that distance was negligible earlier. So it was very easy to define all our terms simply as distance between the drain and the source. We didn't care for very rigorous definitions there. Unfortunately, now when we bring this drain very close to the source, the same depletion region would form here as well, right. Of course I have changed my supply, I have lowered it, but still what will happen is now this depletion region that is being formed around the source and the drain will become a significant fraction of the total channel length, right. So this is, if you look at it, is basically delta L. So the channel length will become L minus delta L for whatever reason, for the reason that is shown here. Okay, not for whatever reason, for multiple reasons which I will show you, right. Now I'll do one more exercise. I'll increase this VD to a higher potential from very small voltage, 0.1 volt, I'll make it VDD. Let's assume that the VDD is 1.8 volt. Now what will happen to this depletion region? I know I didn't discuss it, but if I forward bias a PN junction, the depletion region will come down. If I reverse bias it, it will go up. This is another thing that we will just take for granted, right. So is this body source, okay, let's assume that the body also is grounded for now, by the way, okay. Is this body drain junction forward biased or reverse biased? Reverse biased, right, because I am applying a positive potential to the N plus region and a negative potential ground to the P region, okay. Therefore if I now increase my VD, it makes it worse because this depletion region will go up further. Okay. So this will become delta L minus another delta L prime because of my new thing. So I will say VD equal to VDD, okay, color coding it, correct? So now what happens? Your channel length has come down already, okay, this is just the intuition by the way. Channel length has already come down, which means that my current, what will happen to the current? It will increase because it's mu and Cox W by L, and that L effectively has come down. So it will go up, correct? Look at the other part. This depletion region is what is going to happen in under the channel. So what will happen is there is a depletion region under the channel green here. There is a depletion region that will also form here, correct, in the N plus region. If you remember our PN junction picture that I showed you earlier. But if N plus is in contact with P, the depletion will go far into P region. So therefore this guy, the green region, will actually go very far into the channel and make it much worse, right? So what does this depletion region mean compared to the depletion region that we were forming with the gate? There's really no difference because here also you already have negative space charge regions here in this P, right? So this drain potential that I have applied, positive drain potential that I have applied, has caused a depletion region to go into the channel, already depleting part of the channel, and that's a significant fraction if VD is very high now, which means that what will come down? Threshold voltage of the transistor will come down. Now the gate has to effectively invert only this part of the channel, should deplete and invert only this part of the channel. Again, this is just an intuitive understanding. This is not what happens physically. Physically you have to explain it through energy barriers and all that, which is not necessary for this course. Just understand the intuition behind this and it will be more than sufficient for this course. Okay, that's more important here. So effectively the gate now has to do lesser work in order to invert the channel, and therefore the threshold voltage also will come down, which means now the channel length has come down, the threshold voltage also has come down, and is now a function of what? The drain potential. Earlier you remember that neither the drain current in saturation region nor the threshold voltage was a function of the drain potential, but now that's going to happen, and therefore we have to incorporate all these effects into our short channel device current. Okay, any questions here? Yeah, so basically what I am saying is that I'll maybe draw this a little bigger here so that it's clearer, right? I want to draw the short channel device now a little exaggerated. So this is my N plus, this is my N plus again, right? Now I have my oxide, source is grounded, body also is grounded for my experiment here, gate potential and drain potential. VD is connected to N plus, this is P, okay, body is connected to ground, which means that that is actually a reverse bias PN junction. So if I increase VD, then so first of all at VD equal to 0, you will have a depletion region here around this N plus, okay. Forget about the depletion region in the N plus region, that's not our concern. We are worried about what happens in the channel. So you will have the same distance here also. Now I am going to increase it and make VD equal to VDD. So this depletion region will now go up because it's a higher reverse bias, and therefore you will have this region going all the way here. Now what does this depletion region mean? It means that because this is p type, it's given away a hole, the immobile acceptor atom has become negative or positive? Negative. It's given away a hole, right? So you have negative charges here. Previously, when Vd was 0, my gate had to invert the entire channel from here to here. This was the channel length that the gate had to invert, which means the threshold voltage is going to be defined by how much work it has to do to invert that much of the channel, right? But now, after my Vd has increased, it's come down to this length, L minus delta L prime, because of this applied reverse bias. So now the gate has to invert only so many dopant atoms, and therefore part of the channel has already been depleted by the applied positive drain voltage, thereby reducing the threshold voltage. Of course, now because the two depletion regions have come very close to each other, the effective channel length also has come down by a small fraction. So there is an increase in current by two methods. Delta L is reduced, threshold voltage is also reduced. Okay, so this is just the intuition for short channel effects. Now we will incorporate all of this into our expressions as well. Okay, did that answer your question? Yeah, so what happens is, previously when we derived the equation, all we did was to ensure that the electron had to basically go through this region, reach up to here. It had to go from source to drain, right? That was the net L. But now remember that in the depletion region, the electric field is so high that once it gets there, it will get to the other side very easily. So you are effectively trying to accelerate the electron only in this channel region. Okay? Yeah. So in the given time, I think I can derive one thing, which is basically the we can derive the first short channel effect. Okay, which is basically channel length modulation. Okay, it's called CLM. So we'll take this expression for drain current. Okay. So first question, will this be more severe when Vd is small or when Vd is very large? Vd is very large. So therefore, this will affect the saturation current or linear current. So it's going to affect only the saturation current. So that's a reasonable assumption to make. Okay. So you look at the saturation current, it is half mu n Cox W by L to VGS minus VTH whole square. Okay, this is the long channel equation. Okay, and it's not a function of VDS. That's the main thing. So now what's happening? The effective channel length is becoming smaller. It's becoming L minus delta L. And what is this L minus delta L a function of? What is delta L determined by? The VDS. Now again we resort back to our empirical modeling. We don't worry about what happens exactly physically. We say that this delta L is approximately linear with VDS. It's a fitting parameter. if VDS goes up, delta L should, it is L minus delta L, so delta L should go up. So lambda again is going to be a positive quantity. So I will now replace my ID as half mu n C ox W by L minus delta L, right? And in fact, I will correct this a little bit more accurately now. VGS minus VTH, the whole squared. Okay, so I will do binomial approximation on the denominator. Remove L out. 1 by 1 minus delta L by L. I will write it as 1 plus delta L by L. Right. So this will become half mu n C ox W by L into VGS minus VTH, the whole squared, into 1 plus delta L by L. So this is what we are going to say is lambda VDS, okay, not just the delta L. So let me remove this to avoid any confusion. Okay, this lambda is called the CLM parameter. Channel length modulation parameter. Therefore, this will become ID will become half mu n C ox W by L VGS minus VT whole squared into 1 plus lambda VDS. Okay. So what does this mean in terms of the ID VDS equation that we are talking about? I'll consider the same VGS for a long channel device whose W by L is the same as that of the short channel device. So if L is 1 micron and W is 2 micron, then I will consider L to be 100 nanometer and W to be 200 nanometer. The W by L should be the same, right? And VGS is also the same. That's what we are assuming. So ID versus VDS, the current was basically like this, right? This is long channel. What will happen to a short channel? It will start, it will go up slightly as VDS goes up, because now the depletion region is going farther into the channel, therefore you have delta L, therefore you have more current. Okay, so therefore this current will actually go like this. Remember, it's not like some huge slope, it's a very small slope that you will get there. Okay, this slope is basically, let me just redraw that nicely. This slope is basically lambda.